When we study substitution reactions, whether they're SN1 or SN2, we have to look at several factors. I'm going to just mention them right now, and then of course, as we discover it or discover each reaction or each substitution reaction, we will learn about each one of them in detail. So the effect of alkyl halide structure, what you start with right here, has an effect, whether it's primary, secondary, tertiary, whatever it is. The effect of the leaving group, meaning this bromine right here, had an effect on it. If it wasn't a good leaving group, it would not actually, the reaction would not take place. The effect of the nucleophile, right here. And of course, the solvent and the stereochemistry that results. So let's start with the first one. The first one is SN2, and it stands for substitution, that's the S, nucleophilic, that's the N, and then 2 is bimolecular. And if you recall from the last chapter, that was a reaction where 2 molecules are involved in the transition state. So the reaction rate depends on these 2. So if we look at this generic reaction, and I'm going to mark the leaving group for you and the nucleophile. So if you look at this reaction, you have, in this case, a methyl iodide. So here's your delta plus, and there's your delta minus. This case, I, of course, is your leaving group, Lg. And then here you have the ethoxide ion. That's going to be the nucleophile. The nucleophile. Because the nucleophile replaces the I. Notice the reaction and the product on the other side. So SN2 is a second order reaction. You find that out, of course, experimentally. So I'm not asking you to do that on your own. I wouldn't be able to, so you'd have to do it experimentally. The rate is proportional to the concentration of the alkyl halide and, of course, the concentration of the nucleophile. So again, if you recall, if you double and double both, if you double both, you would actually quadruple. The rate would quadruples. You double one, the rate doubles, and leave the other one constant. Of course, we would double the reaction. So we conclude that this is a second order reaction. The reaction is bimolecular. And of course, we call it SN2, substitution nucleophilic bimolecular. The 2 means bimolecular. What is the mechanism? So I'm going to use a generic reaction. So what happens is that this is a concerted mechanism. One step. So if I have the leaving group right here, or we're going to just, can say Lg or we can say X. Put the H's here, let's say. So what happens is that the nucleophile, and we have to show the nucleophile with its lone pairs. Right there. Attacks the electrophilic carbon, the one with delta plus, remember. And this is delta minus. So forms a bond. Remember what that means, forms a bond. Double-headed arrow, or two-headed arrow, remember, forms a bond with the carbon, and of course the carbon halide bond would break. So you would get, and notice how I'm drawing this. Right here, of course, you have X minus. As we said, that the whatever, where the bond breaks, it takes the electrons with it. Here it is, that's the lone pair. And in this case, that's your product. And there's one thing we need to mention is that this is a back side attack or displacement. We see this all the time from the data. So that's the mechanism. It's a one-step mechanism. Attack happens, the leaving group leaves. In this case, it's X. So here is if we look at the energy diagram, you have, of course, your reactants. Let me use a different color. And of course, you have your products. Right there. So just to mark some things as reaction takes place, this is our activation energy. Of course, down here, this is delta H of the reaction. So of course, the products are more stable than the reactants, and this is our activation energy. So the transition state would look like this. The bond between the nucleophile and the carbon is forming. The bond between the carbon and X, the leaving group, or the halogen, is breaking. So in this case, you would have delta minus, delta minus, and as you see here, reaction takes place. There are important things to remember, that there are no intermediates in here. No intermediates, and the reaction, of course, is exothermic. Very well. Now let's start with the very first thing about those factors. So let's start with the first factor, which is the alkyl halide. This is going to be the end of this video. And then the next video is going to be about something else. If we look at the SN2 reaction, we observe that SN2 reactions are fastest in the following order. So the methyl would be the fastest. Reaction rate would be the fastest, in this case with the methyl. And this would be the slowest. In fact, it actually does not occur. So in SN2, starts with methyl, that would be your fastest, and then it goes to tertiary, almost does not occur, as you will see right here. We have to explain why that is. So if we take some data and look at some data here, imagine, Cl is going to replace Br in an SN2 reaction. Here's your nucleophile. Here is X as the leaving group, and your electrophilic carbon is this attached to this R group. We notice that with methyl, it's very fast. 1,200 is the relative rate. Whereas if you go to primary, you start adding a carbon to that electrophilic carbon, the rate drops significantly. So it's now down to 40. So this is a primary carbon. If you keep it a primary, but you add even more groups, so it becomes more sterically hindered, also it, in this case, of course, it's branched. What is happening here is the rate drops to 16. You make it secondary, the rate drops to 1. Tertiary, it's negligible, almost doesn't take place as we denote. Look how hindered it is down here. So it's negligible. And we have to understand why. And the reasoning behind it is quite simple. If we have, of course, the right pictures here. The nucleophile has to do a backside attack. And here's Cl, that's going to be your nucleophile. So Cl has to find a way to get in and kick the Br out. If you look here, if you have a primary carbon, like in this one right here, which is 40, there is maybe a blockage here by the methyl group, but then the H's are small. So here's a transition state, and then the reaction takes place. So it's a backside attack. However, look now when we go to the tertiary. So this is a primary alkyl halide, and this is, of course, the tertiary. Look at the tertiary. Look how huge these groups are. So you have steric hindrance. The attack doesn't even have a chance to take place. So what happens here is you have high energy transition state due to steric hindrance, or what we call steric strain. But just think of it that, again, it's very difficult for this Cl to get in between an attack because, again, there's a very high transition state occurring. Remember, the higher the transition state, the slower the reaction. So that's what explains why SN2 prefers reactions with less sterically hindered, especially methyl and primary alkyl halides.